cyclic, G has to be cyclic and G has to be cyclic group. All groups whose order is prime number are cyclic groups. They have only trivial subgroups. Namely, identity and full G. No non-trivial subgroup exists. Definitely for these cyclic groups. Cyclic groups whose order is prime, this property is true. So this is an application of this theorem. You understand that, right? If there are divisors, then we should have subgroups. Since prime numbers will not have any divisors, it has no subgroups. Yeah. Someone was asking a question. Okay. Now, for understanding the full implication of this, we have to understand the following thing. If GIH and GJH are two cosets, basically they are two left cosets of H in G, then GIH is equal to GJH, GIH is equal to GJH, or GIH intersection GJH is an empty set. That means if one element is common, then all elements are common, otherwise there are no elements that are common. If you take two cosets, either they are disjoint or they are same. Their intersection cannot be, their intersection either null or the intersection is the full set. Only if we understand this, then we can use this decomposition of the group in terms of subgroup and its cosets. Because I am writing this, but when I write like this, each one is distinct. There is no overlap between this. Okay, so I will leave it for you to prove this. If you have some difficulty, then we can do it in the tutorials. Okay. Also, there is another interesting theorem which can be used to verify whether a given subset is a subgroup or not. Normally, you have to show that it is a group, which means you have to show that the elements of H also satisfy all the four axioms. Okay? So, a subset H of a group is a subgroup if and only if for every Hi Hj in H, Hi inverse Hj is also in H. So you have to just verify this one property. Then you can say that this is a subgroup. So this is a very interesting theorem. Take all pairs and show this is true, then you can show that you don't have to do all the 4 axioms. Okay? So the proof of which also you can try, otherwise we can do it in the tutorials. Okay, so the proof. Now we define what is called normal subgroup or it is also called invariant subgroup. Normal subgroup or invariant subgroup. If H is a subgroup of G, and GIH, the left coset, is equal to right coset for all GI in G minus H, then H is called a normal or invariant a normal subgroup or an invariant subgroup. So what is a normal subgroup? It's a subgroup for which left coset will be same as the right coset for all elements in G but not in H. What happens if I take an element in H? Since H is closed, the coset will be H itself. You cannot generate a distinct element. Okay? So if this condition is satisfied, left coset is same as right coset, then we call it a normal subgroup. Further, we can define what is called a factor group or a quotient group. Factor group or a quotient group. This can be defined for normal subgroups. Let H be a normal subgroup let H be a normal subgroup of G, then we define this as G quotient H is equal to H G1H G2H etc. some GMH. Okay, I can always write G in terms of this, right? We have written already this one when we talked about Lagrange's theorem. So we can write H and distinct cosets of H. H and all its distinct cosets. I am writing with left coset here. You could have written with right coset, because since it is a normal subgroup, it's both are same. Okay, so this this set of sets is itself a group. Okay, this set of sets is a group. What is the operation? The operation is the following. What is the binary composition? So GIH multiplied by GJH, because here two elements are two cosets, remember. Okay, this is equal to GI composition GJ. This is another element, right? That element, take the coset with that element. Okay, now you know this, if you take any two elements here, compose them like this, third element also will be in the same set. So like that you can show all the group axioms. What is the identity here? This has to form a group, that means there should be an identity. What is the identity? If you have to identity, you should have E here, right? So EH is what? H itself. So in this group, identity is H. In this set of sets, identity is H. And inverse, for every GIH, there will be a GI inverse H. Correct? For GIH, there exists GI inverse H, such that GI H multiplied by GI inverse H is equal to GI inverse into H, which is equal to H. This is E, so that is equal to H. So inverse also exists. So we have shown all the group axioms. Associativity is a kind of import of associativity of G, closure, identity, and inverse. So this itself is a group. This kind of a group is called a factor group or a quotient group. Let's look at a simple example. We have considered a set of all integers under addition is a group. Set of all integers under addition is a group. Now let us define H as set of all integers divisible by 3. Let's take set of all integers that are divisible by 3. What is this set? This set is equal to minus 9, minus 6, minus 3, 0, 3, 6, 9, etc. These are all divisible by 3. Is this a subgroup of this under same addition? It's a subgroup, correct? So H plus is a subgroup of Z plus. Now, since it is an abelian group, it's also a normal subgroup, because you add any element from left or right, it doesn't make any difference. So it's also a normal subgroup. It's also a normal subgroup. Now, what are the elements that are in Z but not in this? There are many elements, but let me take 1 is not there, so I can write a coset with 1. So 1 plus H is equal to minus 8, minus 5, minus 2, 1, 4, 7, 10, and so on. This is not a group, but this is a coset. Okay. Now let me take 2 plus H. This will be minus 7, minus 4, minus 1, 2, 5, 8, 11 and so on. What will be 3 plus h? 3 plus h will make this minus 6, minus 3, 0, 3, 6. It is same as h. Notice that 3 plus h is h. Okay, so I will not get any new. Now if I can write this z. I can write this z over h as h comma 1 plus h comma 2 plus h. The entire integers can be written as h 1 plus h 2 plus h. Okay. Now this is a 3 element set. It has to be a cyclic group. Any 3 element set is a cyclic group. This is like h 1 plus h 2 plus h 3 plus h is same as h. So this is called the factor group z divided by h, where h is given as integers divisible by 3. So it is a 3 element group. It's a set of sets. Each set is an infinite set, but the factor group is finite. So many times in physics we use this trick. We have for example in crystallography you have space groups. Space groups are point groups and translations. Translation is an infinite group. So space group is actually an infinite group. Point group is a finite group. But it turns out that if you take the factor group of space group, translation group is a normal subgroup of space group. So you take a factor group of space group to